Okay, let's talk about linear regression. Linear regression is the process of taking data that looks like it basically follows a line and finding the equation of the line that best fits the data. Now, by best fits the data, what that means is finding the line that minimizes the sum of the squared residuals. You don't have to know what that means at this point. We're going to use software that's going to do this for us. So we have this data here. We've done some experiment where we've measured the position of some particle in meters after some time t in seconds. First thing we have to decide is which of these is our independent, or what we call the explanatory variable, and which is the dependent or response variable. Anytime time is one of your variables, it's pretty much always going to be your independent or explanatory variable. So we're going to go with the assumption here that our position depends on time. So time will act like our x and position will act like our y. And we'll measure these in t and x instead of x and y. But you can think like x and y. So the first thing we want to do is plot these data points and see if they do in fact look like a line. If they don't, we can't use linear regression on them. So I've plotted them here. So to do that, I did these in Excel. I created a couple of columns here, time in seconds, position in meters. I even put the titles on there so that now I can just highlight these two rows and I can go insert over to this little bar here and do a scatter plot. And that'll draw a scatter plot for me. And I can make this bigger if I like. I can now go in and add elements onto that. I can add on my titles. So on our horizontal axis, we had time in seconds. On my vertical axis, I had position in meters. I can even change the title because this is really what we're graphing here is position, time versus position, or position versus time. Okay, so now we look at the data and we say, yeah, that does look linear. It looks like it basically follows a line. It's not perfect, but it pretty much follows a line. Now our goal was to find the equation of the line that best fits this data. And Excel will do that for us. I can come here and go to Add Chart Element, go to Trend Line, so add chart element, go to trend line and hit linear. And there's the equator. There is the line that best fits this data. And then once I do that, you have to do it in this order. I've added the line. I can come back here, hit this button again, go down to trend line again. And do more trend line options. And here on this menu, I can click this button, display the equation, and this button, display R squared. I want you to notice we also have this button to set the intercept. If for some reason we want to force the Y-intercept to be some particular number or some point, we have that option right there. So that spit out the equation of my best fit line. Now, I know that I'm not measuring X versus Y. I'm measuring time versus position. So I'm going to go through the trouble of changing these labels here. I'm going to edit this to say T for time and X for position. But you can think of it like X versus Y, T versus X. Now, I could, if I wanted to, just highlight this entire graph and copy and paste that into some Word document. If, say, I were turning in a lab. This is a good way to turn in a lab. There's the equation of our trend line. We have this nice produced graph that's labeled. Okay, so what did we find? We've got position versus time, and here's our best fit line. That has this equation. Remember, we're not doing X and Y, we're doing T for independent variable, time in seconds, and X is our dependent or response variable in meters. Let's talk about what these numbers mean. Remember, the number beside my T here is my slope. What's slope measured in? When I say slope, you think change in Y over change in X. We don't have Y's and X's here. We got T's and X's. So instead of change in Y over change in X, this will be change in X, position, over change in T, time. So my slope here is going to be measured in units of output over units of input. T's in seconds, X is in meters. That slope then is measured in meters per second. So this equation has a slope of about 5 meters per second, a little over 5 meters per second. That's a speed, that's a velocity. So the slope of this trend line here represents the predicted slope or the predicted speed, predicted velocity of this particle. It's moving at about 5 meters per second, a little over 5. And it's increasing. We know it's increasing because it's positive. Notice here, since this data pretty much falls on a line, we have a constant slope. We have a particle here that's moving with constant velocity. Okay, what about the Y-intercept? Remember, intercepts are points, not numbers. So our vertical intercept here will be the point 0, 0.0912, who's negative. So that's our vertical intercept. That means that this model that we've produced, this line of best fit, predicts that when t equals 0, remember these points are t, x, at t equals 0, our position was that number, negative 0.0912 meters. If we wanted to insist that this line of best fit included what we know was our actual position, 0, 0, we could have done that in Excel. But typically we don't. Okay, then we could also find our correlation coefficient using what we have. So Excel spit out this R squared value. We don't have to worry about what R squared represents in this context. What we want to find is R. So we want to take the square root of both sides, but we've got to remember, anytime you take the square root of both sides, you got to put a plus or minus in. I have to look at the picture and figure out whether I want plus or minus. R is not the slope of the line. We already know the slope of the line. But R is related to the slope. And I see that I have a positive slope, so I'm going to have a positive R value. So I'm going to take the square root of both sides here, and I'm going to make the decision that I know I want the positive one because I have a positive slope, and we get this R value. That's called the correlation coefficient. It's a measure of how good this line is. How well the data points fall upon the line. The closer R is to 1 or negative 1, the stronger the correlation. The closer to 0, the weaker the correlation. That R value is very close to 1, so we would say we have a very strong positive, because it's a positive number, correlation. We could use this model here we have to make predictions. So here's my model. If I wanted to predict the position after 5 seconds, when t equals 5, I would just plug in t equals 5. So if I do that, I get this number, 25.1743. So that means the model predicts the particle's position is 25.1743 meters after 5 seconds. Remember, time was measured in seconds, position was measured in meters. Okay, now we can also do this linear regression on the graphing calculator that most of you will have. So in the graphing calculator, the first thing I want to do is turn on what's called diagnostic on. So I would want to go second, 0 to get the catalog there. See, catalog is blue, so second, 0. Scroll all the way down to diagnostic on. That one right there, and then I hit enter twice until it says done. Now I can come into statistics, the stat button right here, hit stat. I want to edit, I want to add in my data, so I'll hit enter. And I've already typed in my data. I want to enter in all my times into L1, all my positions into L2. You can see I've already done that. These do have to have the same length. One of these lists cannot be longer than the other or the calculator is going to get mad at you. Then we go stat, over to calculate, and down to number 8. We could actually use number 4 also, but most statisticians use button 8. That says linear regression A plus BX. I make sure I have the appropriate list there. My X's, my independent variables, my explanatory variable was L1, and my response variable, my dependent variable, was L2. So that was time and position. I hit calculate, leave those others blank, and it will spit out this model. Now we got to be careful and figure out who's playing which role. The number beside x there, see bx, think y equals mx plus b. The number beside x is the slope. So there's my slope. The other value is the y coordinate of the y-intercept. So that will give me the same model. It gives me r squared, and the calculator also gives me r. Excel won't, but the calculator does give you r. Okay, and I think that's a good place to stop.